All right, once again picking up where we left off. A couple more notes here. Since the original function was concave down from -3 to -1 and then concave up between -1 and +1, we did have a point of inflection at x equals -1, and then since it started to go concave down again from 1 to 2, we did have a point of inflection at x equals 1. However, because the derivative didn't go from negative to positive, we didn't have a minimum at x equals 1, and because it didn't go from positive to negative, we don't have a maximum there either. Alright, so I'm going to finish up from 2 to 3. Because the derivative is still negative there, the original function is decreasing, and because the slope of the derivative is negative, the second derivative is negative, and the original function is concave down still. Alright, after that, so that's the same basically as the segment from 1 to 2 there. Now, from 3 to 4, we have a slight change. The original function, the derivative is still negative, so the original function is still decreasing. However, now the slope of the first derivative is positive. So the second derivative is positive, and the original function is concave up. And since we changed from concave down to concave up, we do have another point of inflection. Next, from 4 to 5, at this point, the derivative is positive, so the original function is now increasing. And the slope of the derivative is also positive, so the second derivative is positive and the original function is concave up. Alright, so we're not going to need all of this information by any means to answer part D, but I just want to go through that kind of analysis of the entire graph so that you can see clearly. We know now one more thing is that at x equals 4, because the original function went from decreasing to increasing, or the first derivative went from negative to positive, we do have a relative minimum at x equals 4. And you note that does occur when the first derivative is 0, which is at a critical value. So there are three critical values. One of them is a max, one of them is a min, the other one is neither, it's just a stationary point and happens to be a point of inflection. That will not, does that always happen? It's possible that if it's neither a max or a min, it might be a point of inflection, but I cannot guarantee that at this time. So we have two other points of inflection, which are at x equals -1 and at x equals 3 also. So let's go ahead and finish up part D, which is to sketch the graph. Now the instructions for part D say, suppose that f of 1 is 0. So we do have a point, and we want to sketch the graph only for x equals 0 to x equals 2. So we're only going to use a small part of that information, and what we know from x equals 0 to x equals 2 is that from x equals 0 the function begins decreasing but concave up. At x equals 1 we have the value that f of 1 is equal to 0, and we also know that the derivative is 0 at x equals 1. You can see it reaching up to the x-axis there. So we're going to start off decreasing and concave up. We're going to come in for a smooth landing at a 0 derivative at the point 1 comma 0, and then from there we're going to go decreasing and concave down from x equals 1 to x equals 2. Okay, let me just restate that. We're decreasing and concave down for x equals 0 to x equals 1. We have f of 1 equals 0 and f prime of 1 equals 0. Then we're decreasing and concave up on the interval from 0 to 1. Then we're decreasing and concave down on the interval from 1 to 2. We know that f of 1 equals 0 because that's given to us, and we know f prime of 1 equals 0 because we have a horizontal tangent at x equals 1. Alright, I'm just going to quickly go ahead and graph that information. Decreasing and concave up from 0 to 1, f of 1 is 0. Following this, I'm decreasing and concave down from 1 to 2, and making sure I hit the point 1, 0 and have a horizontal tangent at x equals 1. And that's all there is to that. Okay, so we overdid this problem, but it should be helpful in understanding the ideas here.